Assalamualaikum warahmatullahi wabarakatuh, and a good day to everyone. So I will present my work, which is titled S-shaped inductor implemented in a 12 GHz LCVCO, which is stand for voltage control oscillator for the radio frequency system lah, for RF system. So this is my fellow friends which is involved with this project, and I am actually under the microsystem technology COE, which is from the Faculty of Electronic Engineering Technology lah. Okay, so why is it I'm choosing this 12 gigahertz frequency range? Okay, because we know that in recent years there has been an ever increasing push to achieve a wider bandwidth, higher performance and lower power in RF system, all while increasing the frequency range and decreasing the size of it. Alright, so this trend has been a driver for technology improvement, which have allowed for greater integration of the RF components, which is compared as previously done lah. Okay, so this requirement, which is wider bandwidth, higher performance, right? This requirement has pushing the system to operate in the Ku-band or Ka-band due to the fact that wider bandwidth and higher data rate are easier to achieve at this frequency. So Ku-band and Ka-band is actually from 11 to 18 gigahertz frequency range. So this demands means a higher density of channel and a wider bandwidth per channel are needed lah. Okay, to achieve the performance, to achieve for higher performance and lower power in RF system. Okay, so so for this project, we will implemented the S-shaped inductor into the voltage control oscillator, because we know that VCO is actually the key and critical building in the wireless or optical communication transceiver, because the primary challenge in designing this VCO is actually we need to minimize the phase noise, but at the same time we need also maintaining the smallest power consumption for that, which can be achieved by improving the poor Q factor of the on-chip inductors. Because if we go looking at the equation for phase noise, we can see the relation why we need to improve this Q factor lah, for this on-chip inductor. Okay, so higher Q factor inductors with a high self-resonant frequency are needed to minimize the power consumption as well. And then it also can improve the phase noise of the VCO circuit. So as I said before, so this is actually the relation between phase noise and also the Q factors of inductor here lah, in the tank, in the LCVCO tank. Okay, this equation has been described by the lesson formula. Okay, if we can see here, this is actually the phase noise, and now we are only focusing in this QL, which is the Q tank. Okay, so from this equation it is clearly shows that the phase noise of LCVCO is actually inversely proportional to the square of the Q tank. Okay, so means that it clearly shows that in order to improve the phase noise for this LCVCO, so it's good if we can use the high Q factor LC tank, which is this is actually the effective way lah to lower the phase noise. Alright. While we come up with the inductor design, which is can improve the Q factors of the inductor itself lah. Okay, before that, the Q factors is actually the parameter that characterize the power loss in an inductor, or it can measure its ability to save the energy lah. Okay, so the Q factor itself is actually derived from this pi model, from the spiral inductors, Okay, so when we derive from this spiral inductor, the equation for Q factors is actually omega. Omega is actually equal to 2 pi f. Then we have times with the Ls, which is the inductance, and Rs, which is the inductor lah. Okay, and then times with the substrate loss, and also it times with the self-resonant factors. Okay, so Rs and Ls is actually LS is actually represent the coil equivalent inductance, and RS is actually represent the equivalent resistance, which is caused by the coil metals, this RS, coil metal, and effects caused by the conductor and substrate. And then CS is actually represent the equivalent capacitance due to the interturn capacitance, fringing capacitance, and capacitance due to the coil metals overlap with the underpass metal layers. And the COX is actually represent the capacitive effects of the oxide layer lah. And this R sub and C sub here is actually the substrate resistance and the parasitic capacitance. Okay, so the substrate losses is actually involved with the ohmic losses, which is this ohmic losses in the substrate is actually caused by the displacement current which is induced in the substrate, which is accounted by this substrate resistance, which is R sub, and as well as the C sub here, the parasitic capacitance in the substrate. Okay, which is effect the substrate loss lah. So means that the substrate loss is actually coming from this resistant and capacitance substrate lah. Okay, and then here is actually also we have the substrate loss factor, which is also lowering the inductor Q factors lah. And we can see here also we have this RS. This RS is inversely proportional with this Q factor, so means that it's clearly showing that this resistance is actually lowering the Q factors value lah. So that's why we come up with the S-shaped inductor design, where this S-shaped inductor design can reduce the length of the core inductor coils. Then it can reduce the resistance of the inductors. Then it can improve the Q factors for the inductors. Okay, so this is the S-shaped inductor that we propose, which is this have the geometrical parameters of OD, which is outer diameter, W, which is width, and the T is thickness. So these parameters will be optimized in order to get higher Q factors of inductor lah. Okay, so this inductor have a result of 0.505 nanohenry, which is Q factor is actually 50.22 at 12 gigahertz. So the geometrical parameters that we have to get this Q factor is actually we have the thickness, metal thickness is 5 micrometers, the metal width is 15, and the outer diameter is 320 micrometer. So this inductor will be implemented in the LC tanks in the LCVCO. So now how we implemented this S-shaped inductor in the VCO. So the S-shaped inductor is integrated in the 12 GHz LCVCO as a two-port network, in which the S parameter is used as the electrical properties of the inductor. So we create another file for this S-shaped inductor into the S parameter, so that we can use that to implement it in the VCO lah. Okay, so this is the circuit that we have for the inductor. Okay, so it clearly shows that here we have a pair of cross-coupled PMOS here, cross couple PMOS, which is M1, M2, and we have NMOS as well, where we have M3 and 4. This cross couple will produce the necessary negative impedance to counteract the losses of the LCVCO, which is the main part of this VCO. Okay, so we have L1 is 0.0011 microhenry and capacitance as 0.4. Filters are inserted at the switching pairs at the common source point to resonate in parallel with the capacitance. So this is the noise filter that we are using in order to lower the phase noise of this VCO lah. Okay, so this is the design for the LC tank for this VCO, which is we have, this is 2 NMOS transistor, which is M6 and M7. This is used as a varactor to keep the capacitance low and the loaded Q factor high at higher frequency lah. And then we also integrated or implemented this S-shaped inductor in this LC tank, which is replacing the high Q factor inductors here. So we replace this L, the inductor here, with our S-shaped inductor in order to lower the phase noise for the design for the LCVCO lah. So this is the result, the simulation result that we have when we used our S-shaped inductor lah. So here we can clearly see that the range of the tuning range for this VCO is actually between 11.6 to 12.1, which is in 500 megahertz tuning range lah, which is between 0.5 to 3 volt. So this is the summary table of that. So we can clearly see that our 12 gigahertz is approximately tuning at 12.07, which is at 2 volts lah. Okay, and then for the simulation result for the phase noise, we can see that this is the phase noise versus the offset frequency. Okay, so from here we can see that the phase noise of negative 131.33 decibel per hertz and negative 1.6.71 decibel per hertz at 10 megahertz and 100 megahertz lah. Okay, 10 megahertz and 100 megahertz here. So we can see that the 12 gigahertz operating frequency is approximately 1.5 of the tuning range. Okay, so this is the comparison performance for our LCVCO with previous related work. Okay, so from here we can see that the figure of merits of the VCO based on the offset frequency at 1 megahertz and 10 megahertz is negative 170.30 and negative 1.78.60. Okay, and the summary table shows that in comparison to the VCO used by Islam Monzor in 2020, which is this one. Okay, clearly here we can see that the 12 gigahertz LCVCO reduced the phase noise at the 10 megahertz offset frequency by negative 5.20, which is, if we compare with that result with this lah, we can see that this is our work. All right, here this is our work and this is the Islam Monzor. So we can see that we have improved by negative 5.02 lah. Okay, and as well as this VCO uses less power than VCO from the Y-Wang 2012 lah. Alright, so we can see that we have used the compared here the power, it's actually 93 milliwatt, but here we have 26.96 lah, so we have improved that kind of power and as well as the phase noise lah. Okay, so from this comparison we can see that this work which is 12 gigahertz LCVCO phase noise and power consumption were both improved by the use of an optimized inductors. Okay, so for the commercialization for this component overall component, okay, so we can clearly see that the RF components market is actually expected to develop as a result of consumer electronic usage and the requirement for high-end telecommunication devices. Along with this, also the market expansion for the RF component is also driven by the growing development and innovation in smart sensor devices, which is for the wireless communication as well as the higher performance computing HPC module for a wide range of application fields lah. Okay, since they are crucial for improvement, the expected high bandwidth, which is projected to be the driving force behind many 5G use cases, they are especially more important in the realm of 5G. We also looking at the future for the electric vehicle driving, which will be enhanced by the using for the high speed, high resolution control, which will increase the power efficiency, extend driving range, and improve the EV driving experience. So I think that using our improved component, so we also can commercialize that component into these applications lah in future. Okay, so thank you so much for listening to this video.